When a fully loaded 18-wheeler pulls away from a dead stop on a steep grade, its clutch absorbs somewhere in the neighborhood of 300,000 joules of thermal energy in a matter of seconds. That's roughly the same energy released by detonating a quarter stick of dynamite, and the clutch just soaks it up, dissipates it, and gets ready to do it again. In Formula 1, the scale of the problem shifts to the opposite extreme. Carbon clutch packs no bigger than a saucer begin to engage at over 10,000 RPM, managing the transfer of around 1,000 horsepower while surviving surface temperatures that momentarily spike above 1,000 degrees Celsius. As a relatively small component, it is staggering the amount of energy that is directed through it. But clutches weren't always this capable, and getting from its crude, simple beginnings to the incredible capacity of modern composite clutches took over a century of incremental engineering. This is the story of the clutch. In the late 1800s, the very first automobiles were not much more than motorized carriages, and with this simplicity came the problem of how to connect the violent jerky action of a combustion engine to the drive wheels without causing damage. German inventor Siegfried Marcus, known for creating the first gasoline-powered vehicle, first encountered this problem with his attempts at powering a cart. Built around 1870 in Vienna, Marcus's powered cart required an assistant to physically lift the rear wheels off the ground so they could spin freely while the engine fired. Once it was running, the helper dropped the wheels back down and off it went. While it technically worked, what was missing was some way to gradually and controllably feed the engine's power to the wheels. Carl Benz would derive a solution to the power control problem from the factory floor. In the manufacturing plants of the industrial era, centralized steam engines or water wheels powered long overhead shafts that ran the length of the building. Individual machines were connected to those shafts by looping leather belts around pulleys. When you needed to stop a machine, you slackened the belt. When you needed it running, you retightened it. That principle of controlled slippage became the basis for the clutch. Benz applied the concept directly to his 1886 Patent-Motorwagen. A flat leather belt ran between a drive disc on the engine's output and a countershaft connected to the rear wheels. To sit at idle, the belt rested on a free spinning disc. To get moving, the driver shifted the belt onto the fixed drive disc, and as it gripped tighter, the wheel began to turn. While it was simple, it gave the driver a way to gradually apply power. Before we continue, I'd like to thank Storyblocks, the sponsor of this video. Making a video like this one means tracking down a lot of footage I could never easily acquire myself. Vintage factories, vehicle shots, mechanical close-ups, and slow-motion B-roll. Much of what you've been watching on screen comes from Storyblocks, and they've genuinely become essential to how I produce. Storyblocks brings together over 7 million assets, footage, music, sound effects, templates, and images into a single library, so I'm not bouncing between 5 different platforms trying to find the right shot. And everything in there is 100% human-made, created by real filmmakers and artists around the world. They don't accept generative AI content, which matters to me more than ever. What I lean on hardest is the speed. They've got customizable templates for Premiere Pro, After Effects, and DaVinci, plus a plugin that pulls the library directly into my editor. They say it saves members around 3.5 hours a week, and for my production cycle, that tracks. And everything is royalty-free, pre-licensed, and cleared for monetized YouTube videos, so I'm never second-guessing usage rights. To start telling better stories with the tools I use, head to storyblocks.com/newmind. They're also offering a limited-time discount for my audience, only available through my link. Leather made for a terrible drive material. It was completely at the mercy of the weather. Get it wet, it stretched loose. Let it dry too fast, and it shrank and stiffened. Still, the friction of dry leather on a cast iron pulley was effective, but the heat generated during the slippage needed to get a heavy vehicle rolling would cause the belt to smoke and sometimes glaze over into a hard, slick surface that would barely grip. Sudden torque spikes could snap the belt outright, especially at its laced joints. To keep the leather supple and maintain its grip, early motorists had to periodically dress their belts with a warm mixture of beef tallow and cod liver oil, or apply compounds of castor oil and powdered resin. Even with maintenance, belt failure was a constant problem. That fundamental unreliability pushed engineers to look for a better material that could deliver the same controlled friction without depending on a strip of animal hide to do it. As engine horsepower climbed and vehicles got heavier at the turn of the 20th century, automakers needed a compact, enclosed mechanism that could handle dramatically more torque without failing. From this, the cone clutch was developed. The cone clutch differed from belts in that it used geometry to multiply friction force. The inside of the engine's flywheel was shaped into a shallow, tapered recess, forming the female cone. The driven member was a matching male cone, mounted on a spline shaft connected to the transmission. This male cone was wrapped in a thick band of leather. When the driver released the clutch pedal, a heavy coil spring forced the male cone into the flywheel's tapered recess. Because the contact surfaces were angled, the spring's axial push created a wedging effect, dramatically increasing the outward clamping force on the friction surfaces. This was so effective that at an angle of around 9.5 degrees, the torque holding capacity jumped by a factor of 6 compared to a flat surface. However, cone angles in practice were typically between 12 and 15 degrees, as anything shallower would jam and refuse to disengage. With such an abundance of holding capacity purely from friction, a manageable spring could hold engine torque without any slip at all. To disengage the clutch, the driver pressed the pedal, engaging a thrust bearing that pulled the male cone back along its spline shaft, cutting power transfer instantly. While effective, cone clutches were notorious for grabbing violently. Because the geometry multiplied friction so effectively, the clutch would often bite hard and fast the moment the surfaces touched, producing a sharp jolt that could stall the engine or send a lurch through the entire drivetrain. To reduce the aggressive cone bite, the leather band was kept lubricated with neatsfoot oil, a cattle bone oil that is primarily used today for baseball gloves, saddles, and belts. Getting this lubrication right was tricky, as too much oil would make the clutch slip beyond usability, and too little would not reduce the violent grabbing. This was so critical that commercial oiler cans were specifically introduced for this task. Long-term storage was another limitation of the cone clutch, as if the car sat for any length of time, the leather against the cast iron flywheel could eventually bond, preventing the clutch from releasing. It was not uncommon to wedge a stick between the seat frame and the clutch pedal in order to keep the leather physically separated from the flywheel for long-term storage. One of the bigger limitations of the cone clutch was that it did not scale well. As engines grew into larger multi-cylinder designs, the cone also had to grow with larger diameters and more mass, effectively turning the clutch into a secondary flywheel. When disengaged, this heavy spinning mass refused to slow down, which meant the input shaft of the transmission kept spinning longer after power separation. In the unsynchronized gearboxes of the era, this created destructive gear crunching every time the driver tried to change speed. A way to dramatically increase friction surface area without increasing the diameter or the spinning mass was needed. Solving this problem would lead to the concept of stacking friction surfaces, in which several thin, lightweight discs were positioned on a splined central shaft with alternating plates keyed to the engine side and the transmission side. When the entire stack was compressed with a spring mechanism, the combined surface area of all the plates delivered a large torque capacity in a package that was compact, light, and easy to stop spinning. The most technically noteworthy early version came from Professor Henry Selby Heelshaw, an English engineer who had spent years studying how fluids behave in extremely thin gaps between parallel surfaces. Around 1905, he patented a multi-plate clutch built from thin stamped steel plates, each pressed with a single V-shaped corrugation that was designed to run fully submerged in oil. However, it did not rely on friction for coupling, but rather the viscous drag of the ultra-thin oil film trapped between the plates to transmit power. As the plates were squeezed together, the oil was forced out of the narrowing gaps, and the drive engaged with a smoothness that no other mechanism at the time could match. Like most multi-plate clutches, it also scaled easily to handle more power by simply adding more plates. For example, the 1908 Italo Grand Prix car ran a Heelshaw clutch with 64 plates. The mechanism proved to be so effective that at the 1907 Paris Motor Show, roughly 80% of the cars on display were using Heelshaw clutches. While Heelshaw focused on viscous drag, other variants of the concept worked on material friction, though still ultimately arriving at a similar oil-submerged configuration. William Morris, the founder of Morris Motors, and later the chairman of the British Motor Corporation, devised a mechanism that pressed natural cork inserts into holes drilled through the steel plates. Cork gave an excellent progressive bite, but the friction and heat were enough to set the cork on fire inside the housing. This required the whole assembly to be submerged in engine oil, making it a wet clutch by necessity rather than by design philosophy. His Morse Cowley models ran cork and oil multiplate clutches well into the 1920s. The wet multiplate layout quickly became popular in motorsport. Ettore Bugatti's 1924 Type 35 used a wet multiplate clutch to couple the output of its then advanced roller-bearing straight-8 engine that could rev up to 6,000 RPM. Its variants would go on to accumulate over 1,000 race victories through the late 1920s, making it arguably the most successful race car ever built and demonstrating the wet multiplate clutch's reliability. Today, wet multiplate clutches can be found within automatic transmissions, and as standalone mechanisms remain the standard for nearly every modern motorcycle due to their ability to transmit torque in a tight space and manage the heat of high-revving engines. Dry multiplate versions are still used in motorsports and race bikes, where the oil bath is removed to achieve lighter rotating mass and instantaneous response, though at the cost of smoothness and longevity. Despite their compact size and high torque capacity, the viscous drag of wet multiplate clutches meant that the fluid itself carried enough rotational energy across the stack that the transmission's input shaft never fully stopped spinning, even with the clutch pedal fully depressed. This made engaging first gear from a standstill jarring, particularly with cold, thicker oil. Truly dry friction was needed, but with a single, lightweight plate that could cleanly disconnect power without drag. At the time, no known friction material was capable of surviving the heat of a slipping dry clutch without burning up. By the turn of the century, a materials breakthrough developed by British inventor Herbert Froude would become the basis for the next evolution of the clutch. In 1897, he had founded the company that would become Ferodo, and by 1901 had patented the first commercial brake block built from woven cotton impregnated with bitumen and natural resins. While the material worked well for horse carts, as vehicle speeds climbed, the organic linings charred and wore through quickly. Around 1908, Froude began compounding his linings with asbestos, a fibrous silicate mineral that was cheap, easy to weave, and exceptionally heat resistant. The resulting asbestos bonding lining could absorb the thermal shock of hard slipping without glazing, melting, or disintegrating, and from this, Ferodo began mass marketing asbestos friction products primarily for brakes. In 1910, an American machine shop in Moline, Illinois, would build one of the first clutches based around the new friction material. Borg & Beck had been founded in 1903 by Charles Borg and Marshall Beck to build automatic machinery for making wooden wagon poles, but the business gradually drifted into supplying parts to early automakers. Charles's son, George, working with the firm's chief machinist, patented a single dry plate friction clutch in which a thin friction disc was clamped between the engine's flywheel and a spring-loaded pressure plate. Because the driven disc carried almost no rotational mass, it spun down the instant the pedal was pressed, eliminating the input shaft drag that had plagued both cone and wet multiplate designs. Their first major contract came from the Thomas B. Jeffrey Company of Kenosha, Wisconsin, which was on the verge of losing a military contract due to recurring cone clutch failures on the Jeffrey Quad, a four-wheel drive army truck. The Borg & Beck units reportedly lasted over 2 years in heavy use, a service life that was unheard of at the time. By the time George Borg replaced his father as president and moved the company to Chicago in 1918, Borg & Beck had produced over 200,000 clutches, making it the leading clutch manufacturer in the United States. A decade later, it merged with Warner Gear, Marvel Schubler Carburetor, and Mechanical Universal Joints to form the Borg-Warner Corporation, consolidating much of America's drivetrain supply under one roof. By the end of the First World War, asbestos-lined single-plate clutches had become the standard on every major vehicle class, from cars to tanks. The pairing of asbestos linings with a single-plate dry layout proved so effective, especially in stop-and-go urban conditions, that it went essentially unchallenged for most of the 20th century. By 1956, 85% of the clutches manufactured in the UK were Borg & Beck, with asbestos being the default friction material in nearly every clutch and brake pad worldwide. It wasn't until the carcinogenic nature of airborne asbestos fibers were firmly established, with mesothelioma and other asbestos-related cancers traced back through factory workers and mechanics, that the industry was forced off the material. Ferodo introduced its first non-asbestos semi-metallic pads in 1979, and over the following decades, asbestos was replaced by blends of aramid fibers, steel, copper, wire, glass, and ceramic compounds bonded with phenolic resins. None of these replacements were a direct substitute. No single alternative matched asbestos across all of its properties simultaneously. Aramid fibers like Kevlar offered longer life and were gentler on mating surfaces, but required higher clamping pressures and a long break-in period. Ceramic compounds handled heat well but were expensive and could be brittle. Semi-metallic blends dissipated heat effectively but wore rotors and flywheels faster and generated more noise. What asbestos had done uniquely well was deliver stable friction, high heat resistance, natural insulation, low cost, and easy manufacturability all in one fiber. Replacing it meant engineering composite blends of 5, 10, sometimes even 20 or more ingredients to approximate what a single mineral had done on its own at significantly higher costs. This same family of composite materials can still be found in most road car clutches today. While the single-plate dry clutch was becoming the industry standard by the late 1920s, the mechanism used to clamp it still needed further refinement. In these earlier designs, a ring of 6 to 12 heavy coil springs spaced around the perimeter of the pressure plate provided the clamping force. Coil springs follow a strictly linear load curve, where the more they are compressed, the harder they push back in direct proportion. For a driver sitting at a long traffic light with the pedal down, this meant holding back the full combined force of every spring in the cover at once. At high engine speeds, the problem compounds as centrifugal force caused the individual coil springs to bow outwards, distorting their geometry and reducing clamping pressure when it was needed most, and allowing the clutch to slip under hard acceleration. The solution came from replacing the ring of coils with a single conical spring disc derived from an 1860s French invention known as a Belleville washer. Called a diaphragm spring, it was a thin stamping of high-carbon spring steel with a large central hole and a series of radial slots cut inward from that hole, forming a ring of inward-pointing metal fingers. The outer edge of the spring clamped the pressure against the friction disc, while the fingers in the middle acted as integrated release levers. When the driver pressed the clutch pedal, the throwout bearing pushed against the inner fingertips of the spring. It then pivoted on a support ring that acted as a fulcrum, causing the cone to invert slightly, lifting the outer edge away from the pressure plate and releasing the clamp. Because the spring was a single symmetrical disc, the clamping force distributed evenly across the full face of the pressure plate. This also had the effect of making the whole assembly lighter, easier to balance, and simpler to manufacture. It was also immune to the centrifugal bowing that plagued coil spring designs. The biggest advantage to the design, however, was its nonlinear load curve. A Belleville spring does not push back in proportion to how far it is compressed, but rather the force rises to a peak as the cone is flattened, and then drops off as the cone is pushed past its flat center point towards inversion. In a clutch, this meant that once the driver had pushed the pedal past the initial peak, the force required to hold it down dropped dramatically, making for far less fatiguing operation. The geometry also somewhat compensated for frictional material wear. As the disc thinned over the service life of the clutch, the diaphragm spring's operating position shifted along its load curve in a direction that keeps clamping pressure roughly constant. In contrast, coil spring designs lost clamping force as the friction disc thinned and the springs extended. General Motors fitted an early diaphragm-style pressure plate to its Chevrolet passenger cars and trucks from 1938 through the early 1950s, but the design didn't become a global standard until German supplier Luke commercialized the modern single-plate diaphragm clutch in 1965. The Volkswagen 1600 was the first European production car to use it, and over the following 2 decades, it gradually replaced coil spring clutches on nearly every passenger car built. By the late 1940s, hydraulic torque converters coupled to automatic transmissions had emerged as a mainstream competitor to the clutch. Though because the fluid coupling between engine and transmission was never a rigid mechanical link, a percentage of the engine's output was always lost to slip within the converter itself. In the United States, the majority of new cars were being sold with automatic transmissions by the end of the 1950s, and that share only climbed from there. The 1970s saw industry adoption of lock-up torque converters that bridged the fluid coupling mechanically at cruising speeds, increasing efficiency. By the 1980s, electronic controls were managing shift points in real time based on throttle position, load, and vehicle speed, and 4-speed automatics with overdrive had become standard. For the entirety of this period, the manual clutch itself changed remarkably little. Friction materials moved off asbestos, hydraulic actuation replaced cables, and dual-mass flywheels were added in the 1980s to damp out driveline vibration. but the basic architecture was effectively the same. Still, there were several attempts at a transmission that kept the mechanical efficiency and light rotating mass of a traditional dry single-plate clutch, but automated the operation of both the clutch and the shift forks. Early mechanical attempts at the clutchless manual began to appear in the 1950s. The most widespread was the Saxomat, developed by German supplier Fichtel and Sachs and offered from 1955 onward as an option on Fiat, Saab, Borgward, BMW, Opel, NSU, Lancia, and Volkswagen Beetle models. It used a centrifugal clutch that engaged automatically above idle, paired with a vacuum-operated servo clutch that disengaged when an electronic switch in the gear shift was touched. The moment a driver rested a hand on the lever, engine manifold vacuum was routed to a servo that pulled the clutch fork, allowing the changing of gears without a third pedal. Volkswagen's own Autostick, introduced on the 1968 Beetle, paired a similar vacuum-operated clutch with a torque converter to eliminate stalling at a stop. These systems work, but were mostly marketed to disabled drivers and the convenience market, with performance-oriented buyers mostly ignoring them. It would not be until 1989 for a true high-performance automated manual transmission to emerge. The Ferrari 640, designed by John Barnard, became the first F1 car to race with an electro-hydraulically actuated semi-automatic gearbox operated by paddles behind the steering wheel. The primary motivation was not shift speed, but aerodynamics. Eliminating the internal gear linkage let Barnard narrow the monocoque and tuck in the bodywork, producing the distinctive slim-nosed silhouette that still defines F1 car design today. Through the 1990s and 2000s, the technology trickled down to road cars. The Ferrari 355 F1 of 1997 was the first production Ferrari with a paddle-shifted manual, followed by BMW's sequential manual gearbox or SMG, and Ferrari's own F1 transmission found in the 360 and F430. These were all single-clutch systems in which a computer operates a standard dry single-plate clutch and electro-hydraulically actuated shift forks, managing throttle blip, clutch release, and gear synchronization in milliseconds. In racing context, they were highly effective, but on public roads, they had a peculiar jerkiness that made them worse than a conventional torque converter automatic. Ultimately, no matter how fast a computer could operate a single dry plate clutch, there would always be a momentary break in power flow during a shift. This proved to be especially problematic for turbocharged cars as it would cause boost pressure to collapse during shifts. A method to deliver power continuously while keeping the direct mechanical efficiency of a manual clutch was needed. The concept of shifting gears without breaking torque was first patented in 1935 by French engineer Adolphe Caigres. In 1939, he fitted a prototype dual-clutch unit called the Autoserve to a Citroën Traction Avant, but he ran out of money before a production version could be developed. The idea laid mostly dormant for 2 decades until Smiths Industries commercialized the Easy Drive automatic transmission on the 1961 Hillman Minx, the first true production dual-clutch transmission or DCT. It used 2 electromagnetic clutches managed by analog electronics, but it was unreliable enough that many were eventually replaced with conventional manual gearboxes by frustrated owners. The technology only became viable when Porsche brought it back for racing. Engineers in Weissach had been working on dual-clutch concepts as early as 1964, but development of the modern Porsche PDK truly began in 1981 under engineer Rainer Wurst, specifically to solve the turbo lag problem on their Group C race cars. PDK was first track tested in a 956 in 1983, and in 1986, a 962 fitted with PDK won its first race at Monza. It would take until 2003 for the technology to migrate to road cars when American supplier BorgWarner, working in collaboration with Volkswagen, brought a mass-production dual-clutch system to market in the German-spec Volkswagen Golf Mark IV R32. Called the Direct Shift Gearbox or DSG, their DQ250 transaxle was a 6-speed unit with 2 wet multi-plate clutch packs arranged concentrically inside a single housing. One clutch, K1, handled the odd-numbered gears on one input shaft, while the other, K2, handled the even-numbered gears on a second concentric shaft. While the car was accelerating in any given gear, the transmission's controller pre-selected the next gear on the unloaded shaft, with its shift fork engaged and waiting. The shift itself was just a hydraulically modulated handover where one clutch released as the other clamped down. For a brief window of a few tens of milliseconds, both clutches were intentionally held in a state of controlled micro-slippage, allowing the torque to transfer smoothly between them without ever fully braking. The effect of this action is an uninterrupted gear shift that occurs in under 200 milliseconds. In 2005, the Bugatti Veyron used a 7-speed wet dual-clutch transmission to handle 1,001 horsepower, demonstrating the layout could scale to high power levels. In 2008, Luke introduced the dry-clutch-based DQ200, a 7-speed unit using two single-plate dry clutches arranged side by side instead of concentrically. The dry layout sacrificed torque capacity for lower weight and the elimination of the oil pump losses inherent to wet clutches, making it ideal for small, efficient cars. Within a decade, the dual-clutch transmission had displaced traditional torque converter automatics across most of the Volkswagen Group lineup, and Porsche finally put PDK back into a road car in the 2009 911 Carrera. Today, the dual clutch is the default transmission on nearly every modern supercar, achieving shift times as low as single-digit milliseconds. Even mainstream road cars equipped with dual clutch transmissions routinely shift in around 200 milliseconds. At the extreme end, the Koenigsegg Jesko light-speed transmission abandons the two-clutch layout entirely in favor of 7 wet multi-disc clutches arranged across multiple shafts in a compound gear configuration. Rather than each clutch corresponding to a single gear, the transmission produces 9 forward ratios by opening and closing specific combination of those 7 clutches simultaneously, allowing the car to jump directly to any optimal gear without sequencing through the intermediate ratios. Beyond raw shift speed, modern dual-clutch transmissions also outperform manuals on fuel economy, with Volkswagen claiming roughly 6% better consumption than an equivalent 6-speed manual and 20% better than a traditional torque converter automatic. The modern dual-clutch transmission has effectively become the solution to a century of design compromise in transmission power coupling. For the most part, the electric vehicle has largely rendered the traditional friction clutch obsolete due to electric motors being able to deliver full torque from 0 RPM. However, in all-wheel drive EVs, leaving both motors permanently linked to their axles wastes range since the unpowered motor is dragged along as a generator. To solve this, one of the oldest mechanical clutches in existence, the dog clutch, is used. Formed from a pair of interlocking toothed collars, they engage with zero slip and zero drag. Because of this zero slip characteristic, in an EV, the motor itself acts as the synchronizer, spinning up to perfectly match axle speed in milliseconds before the teeth slide together. Systems like Amsted's Automotive Dynamic Controllable Clutch and Hyundai's Disconnector Actuator system reconnect in as little as 20 milliseconds, latch magnetically so they draw no power once engaged, and recover up to 10 to 20% of driving range over a permanently coupled all-wheel drive layout. Interestingly, after more than a century of refinement through leather belts, cone clutches, wet multiplates, asbestos discs, diaphragm springs, and dual clutch systems, the final iteration in automotive clutch design has been reduced to its most primitive variant.